In the context of solving systems using constant motion, let us look at the two diagrams that have been shown over here. So this is a pulley. All pulleys are smooth, frictionless and massless, and all the strings are light, that is massless and inextensible. So they are so light that we assume that the masses of the strings are zero and they do not contribute any significant gravitational force to be included in the force dynamical equations. So they are ignored basically. So this is the mass m1 and this is the mass m2 that is hanging from the thread. The mass m1 is kept on a frictionless surface. So in this particular case, we can observe that the length of the string is constant. So basically this particular distance, let me call this distance as x1. This particular distance, so mind you, we are always trying to measure distances from a rigid support. So currently we are taking this point, that is the center of the axle of the pulley, to be the rigid support, the fixed support from which we are measuring the distances. So this particular distance happens to be x2. So there is a 2 pi r divided by 4, which is pi r by 2 component. This is a pi r by 2 component present over here, but we are going to ignore that much part of the length of the string, not because it is less in magnitude, but because it is constant. So whenever we are going to differentiate, so we are going to get the derivative to be equal to 0. So the length of the string can be written down over here as x1 plus, I am ignoring pi r by 2, so I get x2. This is equal to the length of the string. So on differentiating this particular equation, I get a1, double differentiating, in fact a1 plus a2 is equal to 0. We have skipped the step when we single differentiate it to get v1 plus v2 equal to 0, because ultimately we want the relationship between the two accelerations. So here the interesting point is, when we use the method of differentiation, then in that case we would have to assume that both the accelerations are going away from the rigid support. So we have to assume accelerations of m1 and m2 to be such that they are going away. Both of them have to go away or both of them have to come towards. So I am assuming both of them are going away. So this is how the accelerations are. Whereas if you do the force dynamical analysis of the mass m1, then in that case you can write down the tension force to be towards the right. So here a counterintuitive equation is going to come, because positive direction we have assumed to be towards the left as far as the mass m1 is concerned. So we are going to get an equation which says minus t is equal to m1a1. This happens to be a counterintuitive equation, but it is correct in the context of using constraint motion relations and constant motion systems, because whenever we differentiate, we have to assume all the accelerations to be away going from the rigid support or all the accelerations to be coming towards the rigid support. This we have seen earlier. Also, the equation for the mass m2, this is an intuitive equation as far as the mass m2 is concerned. This equation is simple. So m2g is in the downward direction and the force of tension T is in the upward direction. So m2g minus T is equal to m2a2. So these are the three equations that can be used to solve this particular system. Now let us say we did not feel like using the method of constraint motion. Then in that case we could have used the intuitive method, which says that the acceleration of m2 I am assuming to be in the downward direction. So let us say this is a, then in that case the acceleration of m1 would have been a towards the right. Here we can still use the intuitive method because the relationship between the accelerations is well known to us. So in that case we could have written m2g minus t is equal to m2a simply, and t is equal to m1a. So these are the two equations which would have given us the value of tension and accelerations. The three equations that we have obtained using constraint method also will give us the same answer. Then why are we using constraint motion equation and using three equations instead of using the simple two equations? Because we are here learning how to apply the method of constraint motion. So in the second diagram, this is the mass m1 that is kept on a smooth horizontal surface, and this is the mass m2. So here also both the pulleys are massless. So one important fact to be realized over here is the tension in this string. Let us say if the tension in this string is T and the tension in this string is also T, then in that case the tension in the string that attaches M2 happens to be equal to 2T. The reason is because the pulley, that is the movable pulley P2, this is the fixed pulley P1, let us say the movable pulley P2 is massless, so the net force on pulley P2 happens to be 0. So tension pulls on object, so on M2 it is going to pull in the upward direction. So if we do the analysis of this particular system, then we can write down that this distance happens to be equal to x1. So this particular distance happens to be equal to x2, and then this distance also happens to be equal to x2. Very interesting fact over here, that the distance from the ceiling to the center of pulley P1, let me write down that distance as d. This distance d happens to be a constant value. This distance d is not changing, only the x2 part of the string is changing. This is very important intuitive understanding. So here we can write down the length of the string to be as x1. So the length of the string is x1 plus x2 plus x2 plus d. This is equal to length of the string. We can write down the length of the string as x1 plus x2 plus x2 plus d. So if we double differentiate this, we'll get a1 plus 2a2 is equal to 0. This will be our first equation. a1 plus 2a2 is equal to 0. The other two equations are force dynamical equations. Again, the value of a1 is assumed to be positive towards the left, and the value of a2 is assumed to be positive downwards, so away from the rigid support. So in such a case, we would have to write minus t is equal to m1 a1, and for m2 we'll have to write m2g minus 2t is equal to m2 a2. So we are not going to bother to solve the equations because that involves just plain mathematics. This is where the physics ends. So these are the three equations which will give us the answer for this particular situation. This situation could have also been intuitively solved. However, I recommend, in order for the listener to be able to apply constraint motion more and more easily, it is important that even situations that are simple to be solved intuitively should be practiced at least once or a few times using the method of constraint motion, so that familiarization with the principles of constraint motion systems and how to write down the constraint motion relations and equations happens smoothly and fast, and thence the listener is able to adopt the method of constraint motion into their own problem solving skills.